Welcome to the Walton Pi. Today I'm going to go through this problem where we are going to prove that this specific analytic function has to be a polynomial. Now, before I get started, if these are the sorts of videos that are helpful, please consider subscribing. It really helps me out. So, let's get started. So let's suppose that f is an analytic function that is defined everywhere in the complex numbers, and that also satisfies the requirement that for every z0 in the complex numbers, at least one coefficient in the expansion of f of z equals the sum from n equals 0 to infinity of cn times z minus z0 raised to the n is equal to 0. We are asked to prove that f is a polynomial. So because f is analytic, we can be able to then conclude that that means that f must also be holomorphic, because analytic and holomorphic functions, those are the same functions in the complex numbers. Okay? So now what we're going to do is we are going to try and figure out how can we show that f has to be a polynomial. So the way we are going to do this is we are going to define a set or a rule that's going to partition the complex numbers. So we are going to say that k sub n is equal to the set of elements, so the set of z's in our complex numbers, such that c sub, or set of z naughts in C, such that c sub n is equal to 0 and c sub j is not equal to 0 for all j less than n. So why are we defining it this way? This is the set of points where in our power series representation of our function at that point, this is going to, k sub n is going to be the set of points where c sub n is the first time that that's going to be a 0 in the expansion. Okay? So that means we have k sub 0, k sub 1, k sub 2. So that means that the union over all k sub n's, n equals 0 to infinity, this is equal to the complex numbers, and furthermore, this is a disjoint union. ki intersect kj is equal to the empty set if I is not equal to j. Because if not, then we'd have a contradiction somewhere. So this forms a perfect partition of the complex numbers. Okay? But furthermore, it's a countable partition of the complex numbers, which is an uncountable set. So that means that since C is uncountable, that means that at least one of our k sets is going to be uncountable as well. So at least one sum of the k sub j's is uncountable. Okay? So we are going to just look at the first one. So let's let k sub j be the first uncountable set. Okay, so we have k sub j as our first uncountable set. Now we're going to try and partition the complex numbers a different way. So we are going to look at, on our complex numbers, we are going to be looking at this grid of unit squares. So all of these are unit squares. We have this nice unit square of stuff. Now, somewhere, there is one of these unit squares that is going to have uncountably many elements from k sub j. So let's say it's this square up there. What we are going to do is we are going to take that square and we are going to break it into 4 pieces. Now, because there's uncountably many things in this one square that belong in kj, that means there must also be uncountably many in one of these other squares. So what we are going to do is we are going to define a way to get a sequence of points in kj that's going to have to converge to something. So what we're doing is we're going to start, here let's actually draw this out by a picture. So here's our first unit square. Somewhere in here is a point that we are going to call z0. Okay? So z0, actually we've already used z, let's maybe change that to w. So there's this point w0 somewhere in there where w0 is in kj. Now this set has uncountably many things, so we are going to break this up into fourths, and one of them we don't know which one, but one of them still has uncountably many things. Figure out which one that one is. Maybe that's this one up here. Then what we're going to do, pick another point, but this time from this new square that is not W0, and then we're going to call that W1. Then we are going to break this square up into fourths, and again, one of these is going to have uncountably many things. Maybe it's this one, and we're going to just keep repeating this process over and over and over forever. So that means we now have a sequence of WNs, and what's more, this sequence must converge. The reason it's going to converge is every single time the radius of the area that we're able to do it in is decreasing, and is strictly decreasing by a factor of 2. And so as we do this, it's going to be forced to converge to something. So we don't know what that is, but it's going to be somewhere in here. So maybe it's going to be this point right there. So that is our point W. And furthermore, because C is dense and all that wonderfulness, we have a sequence of things in an uncountable set that is converging and has a limit point. Okay, so W, that is specifically in our Kj. So that means that Kj is a set with a limit point. Okay, now what's special about this sequence? Well, this sequence satisfies the very nice property that, remember, because we know that f of z is equal to the sum from n equals 0 to infinity of Cn times z minus z naught to the n, let's look at what's the nth derivative of f. So our nth derivative at the point z naught, well, this is equal to n factorial times Cn. Because when we take n derivatives, the only term that the constant term is going to be n factorial times c sub n, and then all the future ones have a z minus z naught to some power, and if we're evaluating it at z naught, that means it's going to be 0 for all of those values. So the only non-zero thing is this, which means that if we look at our nth derivative at each of these wk's, these are all constant. And we have a set that has a limit point where all of them are constant. And so that tells us that by the identity theorem, this function has to be constant on that entire space, on all of C. So that means that for everything, the nth derivative is constant, which means that if we look at the n plus 1th derivative anywhere, that has to be identically 0. And the only function that does that are polynomials. So we just showed that f had to be a polynomial. In fact, we actually showed that everything after kj, oh whoops, all of these should be j's. Oh well. Well, let's just pretend that this is n. But we showed that everything after that has to actually be 0. So there's nothing in any of those sets afterwards. So we didn't actually have a countable collection of sets that formed our partition. We had a finite set of sets that formed our partition, which is absolutely crazy that all of that would actually come from just the restriction that at least one coefficient in the expansion was 0. Isn't that crazy? Like, that is so cool that is actually how stuff has to work, only by assuming that f was analytic, which, to be fair, is actually assuming quite a bit. But like, that's kind of beside the point. But this is really cool. So hopefully this was helpful. Hopefully you're just as excited as I am that we have this really cool result. And if you enjoyed the video, please like and subscribe. Please check out some of my other videos, and please share this with some of your friends. I hope you have a great rest of your day and enjoy the rest of your math.